Thanks for coming along. What I want to talk to you about today is how we can use understanding of sexual reproduction in corals in terms of coral restoration processes and potentially scaling those up in the future. The image in the background is significant because it is one of our representative larval restoration sites showing the growth of the corals over a 5-year period. You can see that that reef system is starting to resemble the reef system instead of a highly degraded one. Basically, we all know that scleractinian reef corals are super important on reefs. They're foundation species, they're ecosystem engineers. And we also know that immense sexual reproduction occurs in natural healthy populations, and that provides mechanisms by which coral communities can be maintained and evolve and recover from natural disturbances. Sex is obviously important in terms of increasing genetic diversity, evolutionary potential and adaptation, and ultimately increased reef resilience. Most corals have a typical biphasic life cycle. Millions of coral larvae are produced, but relatively few adults survive through to reproductive size. And most of the more than 440 species that have been studied formally in terms of sexual reproduction are broadcast spawners. So the diagrams here with all the images show a typical broadcast spawning pattern. The key thing is that there's a whole series of different life stages, and during each of those life stages, fewer and fewer individuals are alive. So you can have literally millions and billions of gametes produced. Relatively few go through to the larval settlement phase. Many of those settled corals die in the first few weeks or months after settlement, and relatively few breeding adults remain at the end of the process. We also have corals that are brooders and have a slightly modified life cycle, and there are species that do both. The key point is that all of those individual life stages are critical links in the chain leading to successful recruitment outcomes. And they're highly sensitive to natural disturbances, and particularly to human-induced disturbances such as pollution events, etc. So what's operating here is very strong selective pressures at each of those stages, resulting ultimately in what we call the type 3 survivorship curve. So most of the corals die when they're very young, and as they grow larger, the survival rates increase over time. We know that coral spawn streaks produce naturally potentially tens, sometimes hundreds of millions of coral larvae with highly variable dispersal patterns and high intrinsic mortality. The interesting thing is we don't actually know what the natural settlement and recruitment success rates are. In good years, it might be as high as 1 in 10,000 larvae that are produced actually result in recruited adults. But it might be as low as 1 in some millions. What we do know is that over time, on healthy reef systems, low but variable recruitment results in some form of decadal scale recovery, at least for the fast-growing species. The global coral crisis is essentially a major issue because the resilience in these natural populations is overwhelmed by chronic human impacts interacting with a series of other disturbances. Not only does that wipe out corals, but you lose the breeding adults out of the population. Therefore, poor larval production, poor recruitment. As a result of that, coral cover declines. And where I'm working in the Philippines is typical of most of Southeast Asia, where most of the reef systems are now highly degraded or under increasing threat. So you can see that in the 1980s we had very high coral cover on these reefs. Typically what you find now is the image on the right-hand side, phase shifted, highly degraded, very low coral cover. And of course the problem for us is that this is happening increasingly on the Great Barrier Reef. The point is, if we're going to intervene, we need to know how, when and where to do it. How do we restore coral populations at large enough scales at sufficient cost? There's obviously increasing global effort that some of our previous speakers have talked about, but there are very varied outcomes. Essentially, there are both asexual and sexual approaches to the problem. We know that typically most of the early work done on this was in small-scale fragmentation and coral gardening approaches. Often they were not effectively monitored, not well set up, and so most of them failed. So very few successes out of that. As people have worked out where the problems are, they've evolved larger nursery scale phases, etc. And as Carly mentioned, this is a major focus of trying to rescue some of the endangered aquapora in the Caribbean. We also know that despite a very large effort over many years, sometimes these asexual-based clonal fragmentation processes don't result in the outcomes you want in the longer term. Mori actually did a very interesting study over a 5-year period with local communities in Okinawa, and he outplanted 151,000 outplants from more than 50 species over a 3-hectare area. But unfortunately, most recently he emailed me and said many of them had died as a result of the 2017 coral bleaching event. And then there's the work that's going on in terms of tissue microfragmentation and fusion, which is increasing the rates at which sufficient biomass might be able to be replaced on these massive corals that normally take more than a decade to grow to sexual reproductive size. My interest is in really the other forms of sexual processes that might occur so that we can actually start to adapt them. We know that there's the potential for increased genetic diversity as a result of using sexual production, and there's larger scale potential. We also know that we can enhance the culture methods in terms of spawning, fertilisation, larval development, etc. And there are a range of different processes that have gone on, and Tali talked about the fact that the Coral Restoration Consortium is a really good model for trying to get all of these people collaborating and discussing with each other the latest innovations that come up and the degree to which they were successful, so we can form a learning community. My interest is in direct larval settlement on the reef, which has the advantage of the larvae deliberately selecting where they might want to live and therefore potentially being better adapted and having a higher survival rate. But it's logistically challenging to do this. My interest in it basically arose from the work we did early on with the coral spawning team, which Russ and Smiles are here. From the discovery of all of these different coral species spawning together, but importantly, the production of these huge larval slicks that occur after these mass spawning events. I played around with some small reef enclosures in the 1980s. Vicky Harriet and I did a report to the Garumpa looking at various options for coral restoration, and in the 1990s I switched attention to looking at how we might start to culture hundreds of thousands or millions of larvae in larger scale tanks, and those tanks there are the prototypes for those that are now being used effectively at CSIM. Andrew did a really interesting pilot study in terms of capturing some coral spawn slick at small scales on Ningaloo Reef, and was able to show massively increased larval settlement, but unfortunately wasn't able to continue monitoring that, so we don't know the recruitment outcomes from that. And more recently, Alistair Edwards and colleagues did a study in Palau where they initially got very high larval settlement rates on artificial reef balls, but then over time the mortality issues coupled with very high natural recruitment swamped the signal. The important thing is, however, that those are on healthy reef systems. Prior to the work that I'm going to tell you about, nobody had actually tried to do this sort of work on highly degraded reef systems or at slightly larger scales, and that's where the ACR and Great Barrier Reef projects come in that I'm going to talk to you about. All 8 of the coral restoration projects that I've led have been successful. There have been 5 in highly degraded reef systems in northern Luzon in the Philippines, and 3 on the Great Barrier Reef in partnership with the Great Barrier Reef Foundation, Great Barrier Reef Marine Park Authority and QPWS. And the potential for some further ones going on this year. In the Philippines, the ACR has funded the project over the last 6 years and extended that recently to 2021. And these reefs are characterised by being highly degraded. Severe blast fishing basically wiped out most of the coral and fish communities, etc. But blast fishing stopped, so they're potentially recoverable. In addition to the 5 larval restoration experiments that we've done there, there's a whole lot of other work that's been ongoing in terms of looking at coral spawning patterns to enable us to capture spawn slicks and rear them on the reef, larval condition experiments, settlement on natural and 3D printed tile surfaces, looking at fish assemblage responses in these areas and socioeconomic values, training, production and media campaigns, etc. The first pilot study was part of Dexter Dela Cruz's PhD, and that was published in Scientific Reports last year. And essentially what we did was set up replicate larval enhancement and control plots, did some benthic surveys to show, yes, there is virtually very little live coral cover. Most of it's covered by algae, and the areas available for settlement of coral larvae on these reef systems are quite small. We raised spawn from 30 Acropora tenuis colonies over 5 days. and deployed about 400,000 larvae into a series of replicate mesh enclosures on the reef for 5-day settlement. Then the enclosures were removed and we looked at what had settled on the settlement tiles, and not surprisingly found moderate rates of settlement on the settlement tiles, but no settlement on the control tiles that didn't have additional larvae added to them. What's really interesting about this project is that Dexter's been able to monitor this for more than 5 years now. So the first 3 years were published in the report last year. But essentially what's happened, you can see the typical survivorship curve where most of the mortality is occurring when they're very young. But what's really interesting, at about 9 months, both on the tiles and on the reef system when they became visible recruits and we could tag them, there's been no mortality since that period. And these corals have now survived 2 bleaching events. So it gives us hope that this process might work. We've had very high rates of growth despite the really poor water quality that occurs at these sites. And these corals became sexually reproductive at only 3 years of age, which was 1 year shorter than had previously been published for that species. We've now had 3 annual spawning events that are occurring, and we're capturing the spawn from these corals each year. So this is the first successful restoration of a breeding population from larvae on a highly degraded reef system. After 3 years, the background image shows you what they look like. All of the asterisk corals are those that are directly settled from larvae. After 4 years, they've grown a little bit more, and then, as I said, after 5 years, that's what it looks like. And each year, they're growing larger and larger. And so they're now dominating the system. And the biomass reproductive unit cost is actually decreasing as they increase in time. In contrast, the control plots, a typical control plot, still looks like that. The reef around it and the control plots are essentially moribund. They're recruitment limited. So unless we start adding these corals back into the system in some way, the system is simply going to continue either in that state or decline further. So in 2016, we used the basics of the same approach from the original pilot study. We captured the spawn from the virgin spawners from the 3-year-old corals, added it to some wild spawn, raised about 4.5 million larvae, and put these into some mesh enclosures on the reef for the settlement period over 5 days. And the image there on the right-hand side is of Dexter, the PhD student, and I adding in about 250,000 larvae in through one of the portals and then spreading those through the enclosure. And as expected, we got very high rates of settlement on the settlement tiles because we deliberately scaled up the density of the larvae. And we've been monitoring the outcomes of that and seen very similar recruitment survival patterns to the first experiment. So after 2 years, we have 250 new recruits on these reef systems and very high ongoing survival and really remarkably high rapid growth rate. And what is really interesting is that some of those colonies grew to more than 20 centimetres in just 2 years, and they became sexually reproductive. So that's a world record in terms of the rates at which acropora are known to be able to reproduce at a minimum age of 2 years. So very rapid life cycle closure on this highly degraded reef system. We've also been monitoring fish assemblage changes, and interestingly, we got a small but significant increase in fish abundance already in response to the increased corals that are on the larval restoration plots earlier this year. And there's a new ACR project that's going to involve Ian McLeod and colleagues from JCU in monitoring those fish assemblages. So we've also been trying to capture coral spawn sticks. So over the last 3 years, we've been developing initially with bamboo rafts and then more highly structured metal enclosures. And we've been successful at rearing coral larvae from these spawn sticks at larger scales on these reef systems. And so that's where the focus of a lot of the work in the Philippines is going to be in coming years. If we move our attention now to the Great Barrier Reef of more relevance to this symposium, the work that was done in the Philippines showed some promise. So in consultation with the Great Barrier Reef Foundation and the Great Barrier Reef Marine Park Authority, we established a proof of concept pilot study in 2016. And the idea here was to look at the effects of different larval densities on recruitment, settlement and recruitment outcomes at Heron Island Reef from the southern Great Barrier Reef. We raised about 1 million Acropora spathulata larvae. You had 4 replicates in each of 3 larval densities and various controls, with and without nets. And not surprisingly, we got highest rates of settlement in the high density, moderate rates of settlement in the medium density, very low in the low density, etc., exactly as you'd predict. And we've been monitoring those outcomes over time in terms of the recruitment rates, survival rates, and I went back about a month ago and looked at the recruitment on the reef and on the tiles, and not surprisingly, they follow a very similar pattern. So larval density drives settlement and recruitment patterns on reef systems. That's been shown experimentally in small-scale lab experiments before. This is the first time it's been shown at this sort of scale on a reef. In 2017, there was a larger experimental outcome, a partnership with the Great Barrier Reef Marine Park Authority, where we went deliberately to larger 100-metre sized larval reef plots at Heron Island and One Tree Island. Logistically very challenging, and you had 4 weeks after funding was announced to get this work done, and 2 weeks of strong winds right after coral spawning wasn't helpful. But we raised 2 million larvae from a range of corals at both Heron and One Tree. We also deployed successfully a larger scale spawn catcher, which is now the basis of what we're going to be doing at larger scales for slick capture, and established larger plots with 100-metre square enclosures. So I designed these as modular units. They can be zipped together to enclose areas up to half a hectare in size in future. And Queensland Parks and Wildlife Service provided essential logistical support. Similar larval settlement rates at both islands, no settlement in control, and we're monitoring the outcomes of those. That's what it looks like after 6 months. Just to finish off with, so we've had 8 reef experiments, on-reef experiments, that show that mass larval restoration is feasible to scales of up to 100 square metres, even on highly degraded reefs, and we're re-establishing breeding populations. That's all very well and good, but it needs to be much larger scale to be meaningful in terms of reef restoration. So the future focus of my projects will be on capturing multi-species coral spawn slicks at large scales and optimising larval deployment times onto the reefs to move up to half hectare and eventually 1 hectare reef enclosures. And in the future, in terms of some collaborative planning and some re-engineering of the process, we should be starting to operate, or aiming to operate, at square kilometre scales. We can overcome that juvenile post-settlement mortality by adding in millions more larvae into the system, improving larval condition before they settle, and potentially with selective breeding and enhanced recruitment as a result of that, as Lean was mentioning previously, to maximise enduring success. But obviously what we do need, this can't be just one individual, it can't be just a single set of skills, it needs to be a collaboration amongst all the key stakeholders to form a learning community. Thanks for listening.